Schrödinger's cat is perhaps one of the most famous thought experiments in the field of quantum mechanics. The experiment centers around the idea of superposition, which suggests that a quantum system can exist in multiple states simultaneously. In the case of Schrödinger's cat, this means that the cat is both alive and dead at the same time. The thought experiment has become a popular way of introducing people to the strange and fascinating world of quantum mechanics, and has inspired numerous debates and discussions among physicists and philosophers alike. Born in Vienna in 1887, Erwin Schrödinger was a brilliant scientist who made significant contributions to many areas of physics, including thermodynamics, statistical mechanics, and relativity. In 1926, he published his famous Schrödinger equation, which described the behavior of quantum systems in terms of wave functions. In the thought experiment, a cat is placed in a box along with a radioactive atom, a Geiger counter, and a vial of poison. The Geiger counter is designed to detect any radiation emitted by the radioactive atom, and when it does so, it triggers the release of the poison. If the atom decays, it emits radiation that triggers the Geiger counter and releases the poison, killing the cat. If the atom does not decay, the cat remains alive. The radioactive atom is in a state of superposition, which means that it is simultaneously decaying and not decaying. As a result, the cat is also in a state of superposition until it is observed. This means that until the box is opened and the cat is observed, it is both alive and dead at the same time. It's important to note that this experiment is purely theoretical, and no actual cats have been harmed in the process. The most striking aspect of Schrödinger's cat is the paradoxical outcome of the experiment. According to quantum mechanics, the cat is both alive and dead until it is observed. This seems to defy common sense and our everyday experience of the world, where objects have definite properties regardless of whether we observe them or not. The paradoxical outcome of Schrödinger's cat can be traced back to the concept of superposition. Because the radioactive atom is in a state of superposition, the cat's fate is also in a state of superposition. This means that the cat is both alive and dead at the same time, until we observe it and collapse the wave function. The superposition principle is a fundamental concept in quantum mechanics that describes the state of a system when it is in multiple possible states at the same time. This means that until the system is observed, it is in a state of superposition, where it has the potential to be in any of its possible states. The Schrödinger's cat experiment highlights the strange and counterintuitive nature of quantum mechanics, and has played a significant role in our understanding of the superposition principle and its implications. The superposition principle has been observed and verified in numerous experiments in quantum mechanics. One example is the double-slit experiment, where a beam of particles is fired at a screen with two slits. The particles are observed to interfere with each other, creating an interference pattern on the screen. This interference pattern can only be explained by the superposition of the particles, where they exist in multiple possible states simultaneously. Another example of the superposition principle in action is in the behavior of subatomic particles such as electrons. These particles can exist in multiple possible states simultaneously, such as different energy levels, until they are observed or measured. This property of electrons has important implications for fields such as quantum computing, where the ability to manipulate and control the superposition of particles is crucial. The significance of the superposition principle extends beyond the theoretical realm, with practical applications in fields such as computing and cryptography. The wave function collapse is a fundamental concept in quantum mechanics that describes the collapse of a particle's superposition state into a definite state upon observation or measurement. When a particle is in a state of superposition, it exists in multiple possible states simultaneously. However, when it is observed or measured, the wave function collapses and it is forced into a definite state. In the context of Schrödinger's cat, the cat is in a state of superposition until it is observed. Once the box is opened and the cat is observed, the wave function collapses and the cat is forced into a definite state of being either alive or dead. The wave function collapse is a crucial concept in quantum mechanics, as it explains how the superposition of particles can be observed and measured in the physical world. It also raises important questions about the role of observation and measurement in the behavior of particles at the subatomic level. The Schrödinger's cat experiment illustrates the role of observation and measurement in determining the behavior of particles at the subatomic level. It shows that the act of observation can force a particle to collapse into a definite state, and that this collapse is an essential part of our understanding of quantum mechanics. The wave function collapse has important implications for fields such as quantum computing and cryptography, where the ability to manipulate and control the behavior of particles at the subatomic level is crucial. In quantum mechanics, the act of observing or measuring a particle can force it to collapse into a definite state, and this collapse is an essential part of our understanding of quantum mechanics. The Schrödinger's cat experiment illustrates the importance of observation and measurement in determining the state of particles at the subatomic level. The cat is in a state of superposition until it is observed, which means that its state is uncertain until it is measured. Once the box is opened and the cat is observed, the wave function collapses and the cat is forced into a definite state of being either alive or dead. The role of observation and measurement in wave function collapse has important implications for our understanding of the quantum world. It suggests that the act of observation can have a direct impact on the behavior of particles, and that our ability to observe and measure particles is crucial to our understanding of their behavior. The wave function collapse is a crucial concept in quantum mechanics that highlights the role of observation and measurement in determining the behavior of particles at the subatomic level. The Schrödinger's cat experiment is an important illustration of this concept, and it has important implications for fields such as quantum computing and cryptography. The Schrödinger's cat experiment has been interpreted in various ways by physicists over the years, each with its own implications for our understanding of quantum mechanics. One of the most well-known interpretations is the Copenhagen interpretation, which suggests that the wave function collapse is a fundamental part of quantum mechanics, and that particles exist in a state of superposition until they are observed. Another interpretation is the many worlds interpretation, which suggests that the act of observation doesn't collapse the wave function, but rather creates multiple universes in which all possible outcomes occur. In this interpretation, the cat is both alive and dead in separate universes, and the observer simply experiences one of these outcomes. A third interpretation is the decoherence interpretation, which suggests that the wave function collapse is not a fundamental part of quantum mechanics, but rather a result of the interaction between particles and their environment. In this interpretation, the cat state becomes definite as a result of its interaction with the radioactive atom and the Geiger counter, rather than the act of observation. These interpretations have important implications for our understanding of the quantum world and our ability to manipulate particles at the subatomic level. The ongoing debate among physicists over the best interpretation of the Schrödinger's cat experiment highlights the complexity and counterintuitive nature of quantum mechanics, and the ongoing efforts to understand this strange and fascinating realm of science. For example, the many worlds interpretation suggests that the act of observation creates multiple universes in which all possible outcomes occur. This challenges our conventional notions of causality and suggests that the future is not predetermined, but rather a result of multiple possible outcomes that occur simultaneously. The Copenhagen interpretation, on the other hand, suggests that particles exist in a state of superposition until they are observed, which challenges our conventional notions of reality and suggests that the act of observation can have a direct impact on the behavior of particles. These interpretations also have important implications for fields such as quantum computing and cryptography. The ability to manipulate particles at the subatomic level is crucial to these fields, and the strange and counterintuitive nature of quantum mechanics has led to the development of new technologies and applications. Some physicists argue that the many worlds interpretation is the most promising, as it provides a simple and elegant solution to the paradox of Schrödinger's cat. Others argue that the Copenhagen interpretation is still the most useful and accurate, as it provides a practical framework for understanding quantum mechanics and has been successfully used to develop new technologies and applications. Its paradoxical nature challenges our conventional notions of causality and determinism, and highlights the complexity and counterintuitive nature of the quantum world. Thank you for watching our video on Schrödinger's cat and the mind-bending world of quantum mechanics. If you found this video interesting and informative, please consider giving it a like and sharing it with your friends and family. And if you haven't already, please subscribe to our channel to stay up to date on our latest videos.